Okay, this video is going to be about RC circuits. Okay, so as it sounds, RC circuits are circuits that have both resistors and capacitors. Okay, so far we've talked about circuits that have only resistors. Okay, so for example, we saw this circuit. Okay, voltage source and some resistance R. So in this circuit, the current is going to be V over R, and the current instantaneously becomes V over R after you connect the circuit. Okay, so and then suppose that you have this circuit V, and this is the capacitance. Then the charge across this capacitor is CV, and it instantaneously becomes CB when you connect the circuit. And as many capacitors as you have in this circuit, they're all going to get a charge of Q instantaneously. It doesn't take any time for the charge to accumulate on the capacitor plates. And same thing in this circuit. If you had more than one resistor, it doesn't matter. The current instantaneously becomes V over the total resistance. Okay, so RC circuits are different. Things are time dependent. Okay, so suppose that you have a circuit that have both a resistance and capacitance. Okay, so suppose this is voltage source V and this is your capacitance C. Then, okay, so initially suppose that this capacitor is not charged. Then what's going to happen in the beginning is that current is going to flowing in the circuit, and because of the current that's flowing in the circuit, this capacitor is going to start charging up. Okay, so as current flows, this capacitor starts getting charged with positive charge. Okay, and this plate starts getting negatively charged, and because it's getting a charge on it, it's going to start developing a potential difference across its plates. Okay, and when that potential difference is equal to the voltage of the battery, then no charge can flow in the circuit, because the potential of the capacitor is going to be blocking the potential of the battery, so no current flows. Okay, so initially there's a current, then the current starts slowing down because the capacitor is getting slowly charged, and then eventually there's going to be no current in the circuit. Okay, so if you were to write down the Kirchhoff's voltage law for this loop, you would say voltage of the battery minus voltage across the resistor minus voltage across the capacitor is equal to 0. Okay, and then it's going to end up being a differential equation. And when you solve the differential equation, you're going to find that the charge across the capacitor as a function of time is equal to the maximum charge times 1 minus e to the minus t over tau. Okay, so t is time, and tau is a very important quantity in RC circuits. Tau is equal to R times C. Okay, and tau means the time constant. Okay, so this means that, so let's see if this makes sense. So we know that if t is equal to 0, the capacitor should not have any charge on it. Okay, so if you put t equal to 0 here, then this becomes 1 minus 1, because e to the 0 is 1. So charge at time t equal to 0 is going to be 0. Okay, according to this equation, which makes sense because we started with a capacitor that was not charged. Okay, and what's going to happen after a very long time, t equal to infinity? So if t is equal to infinity, then it becomes e to the negative infinity, which is 0. So charge at infinity is the maximum charge. Okay, which makes sense because the capacitor is, after a very long time, is going to be holding the maximum charge that it can possibly hold, which is Q max. Okay, more explicitly, it's going to be the capacitance times the voltage across the capacitor after a very long time, Okay, and after a very long time, the voltage across the capacitor is going to be the voltage of the battery. Okay? So you can also rewrite this as Cv times 1 minus e to the minus t over tau. Okay, so that is the charge. What about the voltage across the capacitor? Voltage across the capacitor as a function of time. What would that be? That would be the maximum possible voltage, again times 1 minus e to the minus t over tau. Okay, does this make sense? So this implies that at time t equal to 0, e to the 0 is 1, so 1 minus 1 is 0. So voltage across the capacitor is 0 at time t equal to 0, which makes sense. Okay, and voltage at infinity after a very long time, it becomes, so this term goes to 0, e to the minus t over tau, and it becomes, the voltage across the capacitor becomes just V max, okay, which is the voltage of the battery. And voltage of the battery you can also write as, you know, the charge across the capacitor as divided by the capacitance. What about the current? Okay, it doesn't make sense to say that what is the current in the capacitor. Okay, because the current in this whole circuit is the same everywhere. So we're going to say what is the current as a function of time in this circuit. What is happening to the current? So we said that in the beginning the capacitor is not charged, so there's a lot of current. And then as the capacitor is charged, the current goes down until it is until eventually there's no current. Okay, so what's happening to the current is it's starting out at its maximum value, and instead of 1 minus e to the minus t over tau, it's e to the minus t over tau. Okay, and I max is the voltage of the battery divided by the resistance times e to the minus t over tau. Okay, so so when we have the capacitor in the circuit also with with V over R, which is the normal current term from Ohm's law, you also have this factor of e to the minus t over tau. Okay, graphically what's happening is, let's look at the charge across the capacitor. So if you plot the charge across the capacitor as a function of time, this is the possible Q max, which is also equal to C times V max, right? Which V max is the voltage of the battery. So what happens is it goes up exponentially until it reaches its maximum value. Okay, and so time constant, it determines how fast a circuit is, a capacitor is charging or discharging. Okay, so tau equals 1 is, when for the case when the capacitor is charging, if tau is equal to, or if when t is equal to tau, then it becomes 1 minus e to the minus 1, which is about 37%. Which is about 0.37. Okay, so after one time constant, the capacitor is about 0.37%, 37% of its maximum value. Okay, and then after 2 time constant, it's going to be so much charged, and eventually it's going to be totally charged. Okay, and same thing with the voltage. If you're plotting the voltage across the capacitor, it's gonna start from 0 voltage and it's gonna go up to its maximum voltage, maximum value. Okay, what about the voltage across the resistor? What's gonna happen to that? So we know that V minus VR minus VC is equal to 0. So VR is equal to V minus VC. Okay, so that means if VC is increasing, then VR is decreasing. Okay, so what happens to the voltage across the resistor is that it starts out with having all the voltage across the resistor, and then over time it goes down like this. Okay, and then for the current, I of t, so current also starts at its maximum value and then it goes down over time. Okay, so this is what's happening in a RC circuit when it's charging. Okay, so let's talk about what happens when the circuit is discharging. So suppose you take a capacitor that is fully charged, and then you connect this capacitor with a resistor. Okay, then what's going to happen to the voltage and the charge and the current in this circuit? So let's look at the voltage across the capacitor as a function of time. Okay, so what's going to happen is that, this capacitor is going to cause a current in this direction. Okay, and then this current is going to start depositing positive charges on the negative terminal of the battery and start canceling these charges. Okay, and eventually this capacitor is not going to have any charge on it. And then since it's not going to have any charge on it, the voltage across this capacitor is also going to be 0. And since the voltage is 0, there's going to be no current in the circuit when the capacitor is totally discharged. Okay, so initially the capacitor has, its maximum voltage, which was the voltage that it was charged up to. So in the previous case, we saw that the Vmax was the voltage of the battery. Okay, so it's going to be Vmax times e to the minus t over tau, not 1 minus, because the voltage is going to go down as a function of time. Okay, and then what about the charge across the capacitor? Is that going to go up or down? It's going to go down. So charge is going to be also Qmax times e to the minus t over tau. And Qmax is the capacitance times the voltage that it was charged to, is C times Vmax times e to the minus t over tau. Okay, and then current in the circuit, do you think that's going to go up or down? That's also going to go down. So initially this circuit is going to have a lot of current because the voltage across the capacitor is going to be the voltage across the resistor. Because if you write the Kirchhoff's voltage law for this loop, it's going to be the voltage across the capacitor minus voltage across the resistor is equal to 0. Okay, so voltage across the resistor is the voltage across the capacitor. So if the voltage across the capacitor is decreasing, then it's also decreasing across the resistor. And because of that, the current is also going to decrease because current is V divided by R. Okay, current is directly proportional to the voltage across the resistor. So current is going to be its maximum possible value times e to the minus t over tau, which is also equal to the voltage across the resistor divided by R, and VR and this is the VR max, right? And VR max is going to equal the V max of the capacitor, which was the V of the battery, because we charged it with directly across the battery. Okay, so this is going to be VR max times e to the minus t over tau. Okay, so if you were plotting the charge, voltage, and current as a function of time, then you're going to have some maximum charge across the capacitor, and then the charge is going to go down. Okay, until there is no charge on the capacitor. Okay, and then when t is equal to tau, in this case, e to the minus 1, e to the negative 1 is it's about 0.67. No, sorry, it's 37%. So after one time constant, so your circuit has discharged 37% of its charged. I mean, your capacitor has discharged 37% of its charge. Okay, I think we made a mistake in when we were doing the charging part. We said 37%, but it should have been 63%. So, okay, so, and if we were plotting the voltage across the capacitor, okay, voltage across the capacitor is going to start at its maximum value and then going to go down. And what is the voltage across the resistor going to do? It's going to do exactly the same thing. It's also going to go down because voltage across the resistor is the voltage across the capacitor. Okay, and then the current, if you were plotting that as a function of time in this circuit, is going to start at its maximum value and go down. Okay, so you know, so everything goes down. So current decreases whether the circuit is charging or discharging. The voltage across the capacitor increases if the circuit is charging. It decreases if the circuit is discharging. And same thing with the charge. Okay, charge increases if the capacitor is charging. It decreases when the capacitor is discharging. Okay, so that's a simple RC circuit, charging and discharging. So now let's do a problem that's slightly harder. Okay, suppose you have a voltage source V and some R1 here and a capacitor here and an R2 here. Okay, so what's going to happen in this circuit? Let's analyze the circuit. Okay, so suppose that the circuit was initially not connected. Okay, and the capacitor was totally uncharged to start with. So suppose it was like this. Okay, suppose it was switched off and then you connected the circuit here. Okay, so then what's going to happen to the how is this circuit going to behave? So initially the capacitor has no charge on it, and then eventually it's going to start charging up, and after a very long time it's going to have a lot of charge on it. And when it has a lot of charge on it and when it reaches its maximum voltage, then there's going to be it start going to block the any more buildup. Okay, and because of that it's not going to have any current going through it. So initially, since this capacitor has no charge on it, okay, it's not going to block the current at all. Okay, it's going to let the current flow. So essentially it acts like a short circuit. Okay, so at time t equal to 0, okay, current at time t equal to 0 is going to be only in this part of the circuit. Okay, because the capacitor is not charged, so it is a short circuit. Okay, so all the current goes through this shorted branch. So the current is going to be V divided by R1. Okay, so it's like the R2 is not even here. Okay, and then slowly what happens is the capacitor is gonna start getting charged, and then eventually after it's totally charged up, it's not gonna allow any current to flow through it. Okay, it's gonna block the current. And then since there's not going to be any current flowing through the capacitor, then all the current is going to be flowing through R1 and R2 like this. Okay, so current after a very long time at infinity is going to be V over R1 plus R2. Okay, so we figured out what happens at time t equal to 0, and we figured out what happens at time t equal to infinity as far as current. What about the voltage? What is the voltage across the capacitor at time t equal to 0? Well, we said that capacitor is not charged at all, so voltage across the capacitor at time t equal to 0 is 0. Okay, and what about the charge across the capacitor at time t equal to 0? It is also 0. Okay, because we said that it was a totally uncharged capacitor. What about at infinity? Voltage across the capacitor at infinity. So this capacitor and this resistance are in parallel. Okay, so then that means whatever the voltage is across this R is the voltage across the capacitor also. Right? Okay, so the voltage across R2 is I at infinity that we just found, this value, times R2. Okay, so this is the voltage across R2 and this is also the voltage across the capacitor because they're in parallel. Okay, and what about the charge across the capacitor at infinity? So the charge is going to be the voltage across the capacitor times the capacitance. Okay, so in this case, the capacitor doesn't charge to the value of the voltage of the battery. Okay, the maximum voltage across the capacitor is whatever the voltage is across R2. Okay, so that's the point here. Okay, what about the time constant of this circuit? Okay, what is the time constant? How do we figure that out? So we said that time constant is equal to, R times C, but more generally it's equal to the equivalent R in the circuit times the capacitance. Okay, so what is the equivalent capacitance? The thing to realize is that whether an RC circuit is charging or discharging, its time constant remains the same. Okay, so if suppose that this circuit was discharging, then it would look like this. R1 would be here, you take out the battery, capacitor would be here, and your R2 would be here. Okay, so now what is R equivalent? Obviously. Okay, so now you can see that R1 and R2 are in parallel, and so that would be your R equivalent. So you would say that 1 over R equivalent is equal to 1 over R1 plus 1 over R2. So that would give you your R equivalent, and then you multiply it by C to find your time constant. Okay, and then so we found our time constant, which is this R equivalent times C. So let's say then somebody let's say you were asked to give the voltage and the charge across the capacitor as a function of time. So say you had to say what is Vc of t. So we know that capacitor is going to get charged up to its maximum value, right? So its maximum value is going to be this at infinity after a very long time, times 1 minus e to the minus t over tau. Okay, so t is, tau is this. You're going to find it from this after simplifying this circuit. And Vc is not going to be the voltage of the battery, but this voltage across R2. Okay, and the charge across the capacitor as a function of time, is same thing. Q max, which is Qc at infinity times 1 minus e to the minus t over tau. And if it was a discharging circuit, then we wouldn't have these 1 minuses. Okay, so we played this trick here, to figure out what the time constant would be, and then then you can just intuitively think about it and solve your whole problem. Okay, let's do one more problem. So suppose you have this circuit, a voltage source, and a resistor here, and another resistor here, capacitor here, R1, R2, R4 and R3. Okay, then suppose that this capacitor was not charged at all initially, and then you close the circuit and time t equal to 0, and we have to find what is the voltage across the capacitor at after a very long time. What is going to be its final voltage? Okay, so what's going to happen after a very long time is that capacitor is going to get fully charged. Okay, so then when it's fully charged, there's going to be no current going through the capacitor. Okay, so if there's no current going through the capacitor, then it's like this branch is not even here. Okay, so essentially what the circuit becomes is, it becomes this circuit. Okay, and then capacitor is gone. So this is R4, R3. So then the voltage across the capacitor would be the voltage at this point minus the voltage at this point. Okay, so because the capacitor was here, okay, but then after it gets fully charged up, it becomes an open circuit. It's not even here. Okay, so how do we find the voltage at point A? The voltage at point A, now it becomes a very simple circuit, right? So you have these R2 and R4 in series, R1 and R3 in series, and R1, and this branch is in parallel with this branch. Okay, so you're gonna have some I1 going through here and some I2 going through here. Okay, so I1 is going to be V over R2 plus R4, and I2 is V over R1 plus R3. Okay, and then so if we know the current, then we know that voltage at A is going to be the voltage across R4, which is I1 times R4, right? Because whatever the voltage is at this point, all of it has to fall across R4. And then same thing here. The voltage at VB is going to be I2 times R3. Okay, so the voltage across the capacitor is going to be, when it's fully charged, it's going to be VA minus VB. Okay, so this happens after a very long time, at infinity. Okay, and then what about the time constant for the circuit? Suppose you were asked. Then, it's really hard to say, what's in parallel and what's in series here. But, take out the voltage source. And now let's look at the circuit without the voltage source. It becomes R2 and R1 here. Capacitor here. And R4 and R3 here. Okay, so now you can obviously see that R4, R3 are in series, R2 and R1 are in series, and then together they're in parallel. So your R equivalent for the circuit would be 1 over this branch, which is R1 plus R2, plus 1 over this branch, which is 1 over R3 plus R4. Okay, so that would be your R equivalent, and then your time constant for the circuit would be R equivalent times the capacitance. Okay, so that's it for RC circuits. If you have any questions, please leave a comment.